Yeah,
So thank you everyone and welcome to the Center for Transportation and Logistics Research webinar. I'm Devjit Roy. I'm one of the co-chair of the center. And as you all know, we host distinguished speakers in our webinar forum on a variety of topics related to transportation logistics. We're very excited to have with us today Professor Ashwin Venkataraman, who is a faculty on operations management at the Naveen Jindal School of Management at UT Dallas. And he's going to talk to us on non-parametric demand estimation in the presence of unobserved factors. As you all know, for any transportation problem, we have been traditionally focusing quite a bit on the supply side with different modes of transport, whether it is shipping, trucking, airlines. But I think this is one of the first seminars that we have focusing on the upstream demand side, right? Demand estimation is quite crucial. If demand estimation is quite good, your supply will be quite in sync as well. So I think this topic holds quite significance in our field of transportation logistics. So a bit about Professor Venkataraman. His current research centers on revenue management and pricing. Particularly, he focuses a lot on developing innovative models, then methodologies that use extensive data that's available today, which was not that yesterday probably. And his work has been featured in leading journals, including OR, Management Science, MSOM, and other journals. He holds a MS and PhD in computer science from the Corinth Institute of Mathematical Sciences at New York University. And his thesis also received honorable mention for the Informed Danzig Dissertation Award, which is also quite prestigious. I know that. And he's also earned his BTech in Computer Science and Engineering from IIT Delhi. We all know that. So I think it is a fantastic opportunity to have with us today, Ashwin. Ashwin, we are very fortunate to have you today, and the Zoom is on to you. And to all the participants, we'll be also looking at your Q&A. So please drop your Q&A in the Q&A section. And as I see, and I find it timely, I'll also moderate it. Yeah, so without much delay, it's all the floor, rather Zoom to you, Ashwin. Go for it.
awesome. Thank you so much, Devjit. Yeah, it's a great pleasure to be here. Thank you so much, CTL and Devjit, for the invitation. It would have been great if I could join in person, but maybe next time. Yeah, like I think Devjit already gave some kind of background on the talk. So my work has mostly focused on demand forecasting or demand prediction, and I'm going to talk about one of those papers in this stream of literature. But I guess just to set the context, I want to talk quickly about my broad research interest, which has mainly focused on designing fast and accurate methods to help retailers accurately predict customer demand. And like sort of Devjit already mentioned, this is sort of a very important problem for retailers because these demand predictions feed into key operational decisions like assortment, which is like what set of products I should show to the customers in order to maximize revenue. Similarly, pricing decisions, how should I set prices, again, to maximize revenues or profits. And also inventory decisions, like how much should I order from my suppliers. And of course, these can also feed into sort of transportation and logistics decisions. So demand predictions are very crucial. So if you kind of look at the standard pipeline that any retailer would have in order to estimate or predict customer demand, it would look like the following. So I have availability of historical sales transaction data, which tells me which products were purchased, along with product availability information. So this is like what other products or what other options did the customers have when they were making the purchase. Okay, and this kind of data, as I'll show you, is kind of routinely available. Sort of one of the key things we look at in this literature is what is called a choice model or a demand model. Some of you might be familiar with it, but I'll spend a little bit of time so that if anybody's not familiar, at least you get sort of the high level overview. So this essentially tells me how customers make purchase decisions, right? So it's a model that tells me if I give you a bunch of products, what is the probability that a customer will pick any of the products? Okay, and there are sort of various choice models in the literature. So let's say the retailer will pick one such choice model. And then what I'll do is kind of fit this model. So we'll see these models have parameters. So I'll fit the model to the data using some method. And then I'll use the fitted model to make predictions, right? So these predictions would be, for instance, what happens if I change the price of a product, or what happens if I introduce a new product into the market, or I drop some product from the existing offering, and so on. So these are like sort of all natural prediction decisions that we are interested in. And like I said, of course, these predictions would feed into assortment, pricing, and inventory decisions. Okay, now a lot of the OM literature has focused on sort of the decision side, and rightly so, because that's sort of one of our key core strengths. But before I can optimize any decisions, I also need to fit the model to the data, right? So I need a model with parameters, and then of course I can make my decisions. So that's been basically my focus. So how do we design methods to fit these choice models to data? And specifically, my work has focused on both the parametric models, parametric choice models, as well as non-parametric models. So what are parametric choice models? These are models that impose functional form assumptions on how customers would make these purchase decisions. So if you are familiar with this classical multinomial logit or MNL model, that's an example of a parametric choice model. Okay. However, increasingly there's been focused on non-parametric methods or non-parametric choice models that aim to automatically learn customer preferences just from the data. Okay, so I don't want to impose any a priori assumptions. And this has been like a very sort of fast-growing literature fueled by the increasing availability of data that firms have access to nowadays. Right, I can collect lots of data, both sort of online and offline. So it's sort of well suited to design or well suited to develop these non-parametric. And in this literature or in this stream, my research has also focused on some emerging trends in the literature, like accounting for non-rational behaviors or consideration set models. Again, if any of you is familiar with that. And today's talk would also focus on one of those themes, which has again been traditionally ignored in the operations literature, which is accounting for unobserved factors driving customer demand. Okay, so what is the sort of canonical problem, right? So imagine I'm a retailer and I have a bunch of stores. So by the way, can you see my pointer?
Yes, we can.
Okay, great, yeah. So this is just like a snapshot of Whole Food stores, which is owned by Amazon in the Dallas Fort Worth area where I stay. Right. So, but again, this can be any retailer. You manage a bunch of stores, and sort of canonical prediction problem for you would be you want to predict the demand for each product in each store as a function of the offered assortment. So what is the assortment? Assortment is nothing but the set of products that are available in a particular store. Okay, and of course, this could change over stores, as you might have also encountered. Different stores, even under the same chain, may not offer you exactly the same set of products. And of course, the prices, right? Demand definitely would be impacted by prices. So when you want to solve this problem, one of the key things you want to think about is, yeah, what are the factors that affect demand, right? So what are the factors that would drive customer purchase decisions? And of course, we know the price is an important factor here, but this could also involve other product features, like whether I had a promotion or a discount, right? Then that might influence me to purchase the product. Like brand, like I might be sort of loyal to a specific brand. So the brand name could have some value. What is the size? Is it like a small size or a larger size? Whether I'm buying for my family or just individual consumption, right? So all of these features would definitely impact the purchase decision. And of course, this literature has been around for quite some time, like a couple of decades at least. So there have been sort of more and more sophisticated models that try to leverage these factors and sort of appropriate estimation methods that can capture substitution patterns. Okay, so one of the things that choice models allow us to do is to capture substitution, which is, suppose I go to a store and I wanted to buy a product, but that was not available. Okay, and I'm sure all of you have encountered this, right? Sometimes these are called stockouts. I go to a store and the particular product I wanted to buy was not available. So what choice models allow you to do is to capture what are called substitution patterns, which is, okay, if my preferred product was not available, I can substitute to something else. And sort of how do I substitute, right? So like, let's say you want to buy milk, you definitely want to buy milk. So there's not an option of, let's say, not buying it. So you have to buy something else. Then the question is, okay, which other product do you buy? And depending on how you substitute to the other products or different choice models capture different substitution patterns. And sort of the literature has proposed, like I said, more sophisticated models that can capture more and more complex substitution patterns, which actually fit the data well and are able to better predict customer demand. Okay, so I'm just sort of listing just a small subset of the literature here. It's sort of very vast. Okay, so however, when I describe what I just said, all of these factors would be classified as observed factors, right? So by observe, we mean like, let's say they're available in my data set. So, okay. However, customer demand is also impacted by a lot of unobserved factors. Now, I want to clarify what we mean by unobserved here. By unobserved, I just mean unobserved to me as like the decision maker or the researcher. So these factors are observed by the customers when they make the purchase decisions, and the retailer also would know. Okay. Now, what are some examples, right? So, for instance, maybe there was like some deal or a coupon that was available just in the store, and that was not captured in the data set. Customer demand is also definitely impacted by where the products are located in the store, right? So I have definitely done this before. Like when you're at the sort of checkout counter, you might see like they strategically place like chocolates or other kinds of products right at the checkout counter, and you are sort of tempted to just put them into your basket, right? So where the product is available or where the product is positioned in the store can also definitely impact customer demand. There might be some sort of local demand shocks or some kind of local celebrations or events that might also sort of increase the demand again. And all of these things may not be captured in the data set. Okay. Now, of course, existing literature has tried to account for these unobserved factors, but because they are unobserved, by definition, it's sort of hard to account for them because I only have partial information because they are unobserved, right? I don't know what they were. And existing work has had to make strong parametric assumptions to make the estimation tractable. Okay. Now, if some of you are familiar with this BLP literature, Berry, Levinson, and Peck, they were these three authors that proposed this seminal paper that can account for these unobserved factors, but that method has some issues, as I'll talk about later. Okay, so one argument might be, okay, maybe these unobserved factors are not that important, right? So I can just kind of ignore them. However, as I'll show you towards the end of the talk, it is actually very important to account for them in order to sort of improve the quality of your predictions. Okay, so with that sort of motivation, in this work, we present a scalable non-parametric method to deal with unobserved factors that is practical, right? So what do I mean by practical? It can handle large-scale transaction data from thousands of stores, right? So I have lots of stores that, let's say, a retailer might manage, and I have large amounts of transaction data, like millions of transactions in different stores. So this kind of method is scalable, so it can deal with these large size data sets. Our method can account for varying product assortments. So this I kind of already hinted at, that different stores might have different product availability. And in fact, even in the same store, product availability might change over time, right? So today you see some set of products, tomorrow you go to the same store, some products are stocked out or some new product has been added. So this availability of products can change. And I'll again sort of talk about this, that existing literature is not able to fully account for this sort of dynamic patterns of assortments. And then the third sort of issue that existing work is kind of affected by is what are called like market share estimate, right? So in practice, if you look at stores, right, if you look at like a week or a day, there are only so many customers coming in, right? Finitely many customers coming in. So these are not indicative of your market share, which is like in the overall population, what is the fraction of people that prefer each product? So these are called sort of finite sample errors. And existing literature also sort of has ignored this aspect. They assume that my estimates are actually perfect. So the custom population or the number of purchases that I observe is very large, right? Now, this could be true if you look at a very long time horizon, But what we are interested in, like, let's say, weekly sales transaction data or even daily, so then this assumption clearly doesn't hold. So your method should be robust to these finite sample errors. And again, I'll show that our method indeed is, right? So like, yeah, I already mentioned this. Our method will be robust to varying numbers of sales transaction data, as well as various ground truth models, right? So that is definitely a feature of these non-parametric methods. So I mentioned this in the beginning. Parametric methods impose a priori assumptions, but the issue with those models could be that it is misspecified, which means it does not, your ground truth does not agree or sort of match what you assumed. And that's why non-parametric methods are desirable, because they can sort of automatically learn the right distribution, the right model. So showing this kind of robustness is actually very important for non-parametric methods. And we demonstrate that both empirically as well as theoretically. Okay, and of course, I'll touch on these aspects. And then finally, like sort of the punchline, like I mentioned, is it's very important to control for these unobserved factors. Okay, so if you account for them, you can get up to 63% improvement in prediction accuracy. Now, I'll talk about what sort of precise metric we use, but the key sort of point here is that this is even using the same data. Okay, so I don't have to go out and collect more data to get this improvement. Okay, so of course, maybe you can say if I get more data, potentially if I learn the right kind of patterns, I can have better predictions. But sort of the key message here is, even if you just use the same data set, just by having a way to account for these unobserved factors that are not present in the data set, you can significantly boost your prediction accuracy. Okay. And of course, like I mentioned, your final goal is not just to improve the predictions, you also want to leverage them to have better decisions. And I'll show that sort of that also happens when you account for these unobserved factors, right? So you actually get better pricing and promotion decisions. So you might say that, okay, I don't just care about prediction accuracy, I care about decisions, but even for decisions, it's important to account for these unobserved factors. Okay, so that's sort of the main contributions. So these would be like sort of the take-home messages from the talk. Any questions so far? Probably not. This is
Not
more,
really at this
yeah.
point, no.
Okay, sure, yeah. Okay, cool. So I'll then sort of dive into the details now. So the first thing I wanted to just talk about was, this is sort of very standard data in demand prediction literature in revenue management. But again, I'm not sure if sort of everybody's familiar, so I'll just spend a little bit of time talking about what is the data that we assume, right? So the format of the data would be aggregated sales counts across different stores. Okay, and these would be sales counts for substitutable products. So choice models typically think about substitutable products in some specific product category, right? So let's say, as an example, coffee. So imagine that I am a retailer. I have a sort of product universe of n products. So these could be like different coffee brands that I'm going to sell. And the kind of data that I have is as follows, right? So for each store, I will have the following kind of information. So imagine this is my first store, and I'm using T to denote the store. So in the first store, I am going to see products 1, 2, and 3. So the retailer decided that they're going to show products 1, 2, and 3, or they're going to stock products 1, 2, and 3. And then for each of these products, I have some feature information, right? So again, it's not important to worry about this notation. Just think about this. So this is that for the first product, the price was $10, and let's say it was like light roast. And then what is the size or the volume, right? 500 grams. And of course, I could have other features about the specific product. And what is this? This is how many customers purchased that particular product in that particular store. So let's say I assume I observe 30 purchases. Similarly, for the second product, I have some information about the product, like the price, medium roast, and 300 grams, and so on, right? And again, I observe some sales for those products. Okay. Now, if you look at a different store, let's say store 2, that might offer only products 1 and 2, right? And again, this is possible because stores or retailers are making these assortment decisions, trying to optimize for revenue, right? So they might realize that the customers that are coming to store 2 have sort of more preference for brands 1 and 2 or products 1 and 2. So this kind of variability across stores is very common. Okay, so again, this is just an example. That here maybe I just see products 1 and 2. And also another thing to note is that this is the second product, right, which is common in both stores, but I might see it has a larger price in store 2, right? And again, this is sort of allowed because the retailer can set different prices even for the same product across stores. Okay, again, if there is sort of no regulation, this is possible. Okay, and similarly, I observe some sales, and then for store 3, maybe the assortment is 1, 2, and 4, right? So now I have a dark roast coffee also, and so on, right? So now this kind of data set is very standard, right? So when you go to a supermarket, we scan our sort of products at the checkout counter. So all of this aggregated information is readily available to the retailer. And product features are also available, right? When you kind of scan the product, you know what the product was. So you would know information about the product, like the price, like other features. Okay, so this is sort of very standard in this literature. So the way we're going to sort of denote it is, again, it's not super important to remember all this notation, but essentially ST is the assortment that is offered in store T. So this is going to be a subset of all the products. So this is the universe of all products. XJT, so this was this notation, is the set of features for product J in store T. Okay. And then the number of sales of product J in store T would be this NJT. Okay, so that's the notation I've been using. Okay, so again, this is sort of very standard data set. Any questions about the data?
I don't see anything in the chat, but yeah, if anybody has any questions, please put them in the Q&A.
Yeah, I think, yeah, it's good to have questions while I'm talking. Otherwise, it's sort of hard to keep track for you.
Yeah,
also.
but just I had one question on the feature side, right? So one is, of course, the product features, but there could be features also from the economy and other things, which is common across all the products, right? So can we add on top of it other features as well?
Yes. Yeah. So yeah, here I'm just giving an example, but you might even have sometimes customer features.
Yeah.
Right. So sort of in this setting, we are going to assume more like an aggregated data setting. So we don't have access to customer features. But yes, you're right about like some store level information that is common to all the products. I can just add it as another feature. Yes, that's possible. So that really depends on sort of the model specification, what kind of features you want to, what kind of features you think is important for the customer choice. So yes, but those can be added.
All right.
Okay. So great. So that's the data that I have, right? And if you remember like the original picture, I have this historical data. So this is how the data looks like. Then I have this choice model or the demand model, which tells me, okay, how are customers actually making purchase decisions? Okay, and again, the choice model that we're going to assume falls into this random utility maximization or RAM class of choice models, where sort of the key assumption is that each customer, and let's say we denote customer by I, is going to sample some parameter, omega I, based on some distribution, let's say Q, and then I'm going to compute utilities for each product, right? So UIJT would be the utility for customer I for product J in store T. And that's just like a linear combination of the features. So omega I transpose XJT, a weighted sum of the features, plus some error term. Okay. So that's why you have the random utility, because there's always some kind of idiosyncratic or unobserved, unobserved. How should I say? I want to not confuse this unobserved with the other one, but this is at a customer level. So yeah, there's always some idiosyncratic component from the customer's viewpoint, which is
like
not
fixed effects kind of a thing.
Say that again.
More like fixed effects from the customer point of view, something on that side. Customer level
Yeah, I guess,
system.
yeah, it could capture anything that is not sort of in the data. And this also allows the same customer to choose different products in each visit, right? Because sometimes I go to a store, I might just want to explore, so I might try something else, right? And if you just assume like a deterministic utility, then that cannot be captured. So we
Wow.
always sort of allow this kind of randomness to be able to capture like real world data.
There are a few questions at this
So
point,
yeah,
Ashwin.
yeah.
One question is on, I think it's more of a check whether promotion will go as a feature, both price discount and display, etc.
Yes,
Some
that could go as a feature. Yeah.
feature. And the second question is on how do you rationalize for different customer purchasing power by region? Again, that could be probably a variable that you could add to all the transactions, right? Have some market power parity purchase or anything on that.
Yeah, I guess, yeah, those kind of things could be captured, yeah, based on if you have that information about where the store is located in sort of a particular city, or even
Yeah,
within the city, you have different zones. You can kind of do this analysis, yeah, separately for each zone, because yeah, there might be sort of variations across zones, or yeah, you can just add it as like features in your these X's. So,
sure, sure. Mm-hmm.
so again, this is sort of like very sort of abstract, and or I shouldn't say abstract, right? Well, sort of very general, and then depending on sort of the specific settings, you can add any features or any other information that you deem is going to be important.
Mm-hmm.
Uh, yeah. So, and then like we assume customers are utility maximizers, so they will purchase the product which has the largest realized utility, right? So that would be, let's say, denoted like this. And depending on what functional form assumption you make for this error term, you lead to different choice models in the literature. So, sort of the most common choice model is you assume that these error terms are standard Gumbel distributed. So, you have this Gumbel or extreme value distribution. If you assume that, then you get the standard MNL choice probability that some of you might have encountered. So, this tells me that the probability of choosing a particular product J from some assortment ST has this form. So it is proportional to the deterministic utility of product J. And you kind of normalize it by this is also called the attraction value of all the other products that are offered. Okay, so this is like the standard MNL choice probability that comes from imposing that these error terms are ID standard GUM.
Sure. I should
Okay,
respond
and
to a few
yeah.
questions. I think one is a quite basic question. How do you define utility? That is something.
How to find utilities?
How do you define
So
customer
yeah, so
utility? Yeah.
I'll exactly talk about that. Like, how do we estimate utilities? That's sort of the sort of key goal here, but not utilities directly, because yes, we don't observe the utilities, and I'll talk about that just
Okay.
like in a
And there
couple
are
of.
two follow-up questions also related to previous slide, I guess, is can we build such models for essential goods as well? For example, substitutionality among vegetables and fruit categories.
Yes, so like I'll talk about different product categories in my case study, but there we have like categories like sort of coffee, milk. I don't think we had like a grocery category, like sort of fresh produce. But I mean, yeah. So at least at a high level, I would say yes, but you might have to worry about like some aspect of perishability and so on. So like this news vendor model for perishable goods, right? So that might impact maybe like the time horizon of your analysis. So here, like the products that we're going to talk about are sort of not perishable. Like, I mean, they have, it could be milk. So of course it's perishable, but it's like, let's say a longer kind of cycle. But sort of fresh produce, like sort of vegetables and fruits, yeah, I guess conceptually, yes, but you might have to sort of narrow down your sort of analysis horizon.
Yeah, yeah. And does your model also capture the correlation among stores with the competition between stores as well? That is another
So
question. Yeah.
here, No, we don't explicitly model any competition. So here we are just sort of looking at, sort of a single firm and how are they setting prices. So it's like a centralized setting. So they can set prices across different stores, and they might take into account cannibalization and so on. But yeah, we are not looking at competition between different stores here. But there are like papers that try to account for competition also.
All right.
Yeah.
Sure.
So great. Yeah, all are sort of great questions. So yeah, so like I said, the MNL model is by far sort of the most commonly and widely used choice model in the literature. And actually, what I described is not just an MNL model, it's actually a mixture of MNL or mixture of logit model, because you allow different customers to have different preference weights or coefficients, right? So here, I'm allowing customer I to have a different weight for, let's say, if one of the features is price, each customer can have a different price sensitivity or price coefficient. So this allows me to capture heterogeneity in customer preferences, and sort of this is this is a more sort of practical model, because in practice customers are of course heterogeneous in their in their preferences, and also the nice feature about this choice model is can approximate any choice model in this RUM class. Okay, and this RUM class is again by far the most widely studied choice model. So we sort of go with that choice model. And yeah, like I said earlier, our goal would be to estimate this distribution Q. Okay, so what I observe is this data, right? I observe the sales, I observe the features, I observe the assortments. What I want to estimate is this distribution Q. So going back to the question on how to estimate utilities, so we are not going to directly estimate utilities, but I'm going to estimate this distribution. So I know how my parameters omega are distributed in the population. So I can sort of come up with a distribution of utilities. But we're not estimating individual utilities for each customer because they are unobserved, right? We only observe the purchase decision, right? So when we go to a store, or the data only tells me which product the customer purchased, right? It does not tell me, oh, customer had this utility for this product, some other utility for other products, right? So utilities are only in customers' minds. What we observe are the purchases, but we'll assume that the way the customers are making purchases is based on this utility model. And so the goal would be to estimate the distribution of these parameters, which tells me the distribution of preferences. Does that sort of answer? Hopefully that answers the question on the estimation. So that's what we're going to estimate here, the distribution Q.
So there's an additional question here, Ashwin, is on the, again, scope of the model. Mm-hmm. So does the model also consider new product introductions? For example, you start off with time one, but in later time periods, a new product enters the market, right? To the same store. And how will that play a role here in the whole estimation?
Yeah, so I guess the way we are thinking about it is like this is like entire product universe. So yeah, so for instance, like if you're looking at a specific month and then you have weekly data, and then maybe in week 3 you see that there was a new product that was introduced, then I think as long as, again, we assume all are substitutable products, right? So we are not going to be able to capture any complementary relationships. But imagine if it's like another brand of coffee, then I think as long as you account for all the products in your universe, and you sort of, I guess we are not modeling the decision to introduce a new product, but if your data just has some new product that was introduced and you observe sales for that, it should be fine. But we are not sort of, at least in this work, we are not thinking of making those decisions, right? So like I said, this work is more on the prediction side. Sure. Of course, the predictions feed into decisions of like assortment or new product introduction. But so we are just focusing on estimation or prediction given sort of some historical data.
Fantastic. And I think, sorry, there is a follow-up question on the on the error term that you had in your model. I think the question goes back whether it is positive or negative, whether it is same for each utility. I think for same for each customer, probably not. So
No, I mean, yeah. So this depends on the customer, right? So,
yeah,
and these are IID, yeah. So for different products, it could be different, but they are kind of randomly drawn from some distribution. Yeah, they can be positive or negative.
fair enough. You can go ahead.
So okay, so yeah, so that would be the goal. And actually, so far, I should say this is all in some sense like existing literature in the sense that this is what prior literature before our paper would do, right? This is the data, and you want to estimate this particular distribution. Now, what we sort of introduce is this notion of unobserved factors, right? So this is again just summarizing what I had in the previous slide. So the data, the utility model, and the goal, right? To estimate this distribution. But like I said, in practice, my data rarely includes all of the factors driving the demand, right? So if you actually look at the utility that the customer is forming, there is this hidden term, which we call xijt, that also impacts utility. Okay, and this is going to be called an unobserved factor, or UF for short. Okay, now again, this goes back to what I said, right? Unobserved is only for me as the modeler or the researcher, right? The customer does observe that when you're making the decision. So that's why I'm able to write this in the utility. But for me, this xi is not in the data, right? So the data will not have xi. Okay. And if you look at my notation, I just have xijt here, not xijt, which I had here, right? And the reason for that is I'm going to deal with aggregated data, right? So I don't have access to individual customer data. So I don't know a specific customer, what product they purchased. I just know in aggregate what were the total number of purchases. So this makes sense because this is sort of only for product J and store T at an aggregate level. And the other sort of assumption you see here is, I should have mentioned this, but all the vectors are denoted in bold notation, right? So X is a vector of features, omega is a vector of parameters, but xijt is like it's a scalar, right? So it's like a single number that is unknown. Now, this is a standard assumption in the literature, but as you'll see that our framework actually allows one to estimate a vector of unobserved factors. So I could have multiple unobserved factors, right? Like I gave examples like the shelf space or in-store promotions or deals. So in practice, there could be multitude of unobserved factors that are driving the customer demand. So for now, you can just think of this as the aggregate impact of all of those unobserved factors. But like potentially there's scope to sort of use our framework to capture multiple observed factors. But again, for this work, this is the standard assumption in the literature, so that's what we are going to deal with. Okay, so that's sort of the addition. So now your estimation problem will not just be of estimating Q, but also these unobserved factors. Okay, but the data, of course, is still the same as before. Okay, so that's sort of the key change now. Like you have to estimate both Q and xi together from the same data. Okay, and that's a problem we would like to solve. Okay. So yeah, Devjit, any question?
Yeah, just one question. I think it's on the data type, which is trivial, which is what kind of data type? Is it panel or cross-sectional? Is the data collected from all stores over a period of time? I think that's true, right?
Yeah, it's not panel data. Like, yeah, we don't have individual customer data. It's like, yeah, more cross-sectional. And yeah, again, I'm actually not giving the full details of the data, but yes, it is across stores, but it could also be repeated observations in stores. So for instance, in the first week in a particular store, how many sales, then the second week. And actually, I'll talk about that in the case study that I do at the end.
So do
But
you
yes, it is
also have the
across
customer?
stores,
Do you also have the
across
customer
time.
ID? Do you also have the customer ID?
No, we don't have the customer ID because it's aggregated data. So I
So
don't
then,
know.
how do you find out the fixed effects then here, which is the
So there are no customer fixed effects, right? There are only product J and T. There's no
but
I.
you have omega I, right? Which
Yeah.
is
So
the
omega
customer.
I is the parameters that I have to estimate. So that we can estimate. So I guess the question is, I yeah, this is just for notation. What you're going to actually estimate in the end is just this distribution Q.
Mm-hmm.
So it will just be a distribution over all possible omegas. So I cannot tie it to a particular customer ID, but just based on the patterns or the purchase that you see, you know that omega is distributed like this in the population. Like
Okay.
if that makes sense. So, but
Yeah.
if you had panel data, yes, you could try to estimate like individual customer preferences. But yeah, in this work, again, aggregated data estimation is also standard in the literature. So we are going to focus on that.
Got it. Got it. Sure.
Okay. So yeah, so our goal is to estimate Q and Xi, like I said, right? And the way we are going to do it is to have a non-parametric estimation method, like I mentioned in the title of the talk. So we are not going to impose any assumptions on Q, right? So Q is a distribution, right? So Q can be, let's say, a normal distribution, exponential distribution, any kind of distribution that sort of we are familiar with. But instead of imposing that Q has to be of a specific form, that would be like a parametric estimation. And like I said, there can always be issues of misspecification. Like you assume it's a normal distribution, but in practice, you don't know how customers are making decisions, right? You don't know how the utilities are distributed. So there's always a chance that there's a mismatch. So ideally, what you want to do is you want to leave Q unrestricted. You want to search for the best possible Q across all possible mixing distributions. So this actually Q is called a mixing distribution because it sort of mixes the customer preferences in the population. So what is the formulation, right? So what I'm going to do is I'm going to find the best Q and Xi. Those are the things I have to estimate that best fit the data. Okay. And the fit to the data will be measured using some kind of loss function that will measure the mismatch between the observed sales counts and the predicted sales counts under the model. Okay, so I'll give an example of the loss function in sort of a minute. And what is the constraint? The only constraint I have is that Q is a valid distribution. Okay, so this is what it's telling me. Right? It's like a valid probability density that it integrates to 1 and it is non-negative, right? So that's the only assumption or only constraint I have. So what this is telling us is that this is searching over all possible Qs, right? Remember, I'm not saying like Q is a normal or anything here. So I'm searching for all possible Qs. And D here is just the number of observed factors. Okay. So that's what I'm going to estimate. Or that's what, let's say, the goal I'm planning to estimate. Okay. Now, what is an example of this loss function? I'm sure all of you have seen maximum likelihood estimation. So in maximum likelihood estimation, you maximize the log likelihood. Here I'm looking at the minimization problem. So I'm going to look at the negative log likelihood, right? Because I want to minimize. And that is also called the log likelihood loss. So this is how it is written, right? So you sum over all the products and all the stores. You have the NJD, which recall was the number of sales of product J in store T. And then you multiply it by log of the purchase probability, right? So this term inside is actually nothing but the predicted purchase probability of product J in store T. How do you get that? You remember this was just the MNL kernel. So this is for a fixed omega. What is your choice probability? And then you integrate it over all possible choices of omega, right? Because omega is not fixed. It comes from some distribution. So you sort of integrate it over all possible choices of omega. So this is exactly the probability that a customer will purchase product J from store T under this choice model. Okay. So this is the mixed logit choice probability. Again, this is like standard and like this is nothing new here. This is just how we write it. Okay, of course, the novelty is like these Xis. I also have to estimate these Xis, whereas existing literature ignores these Xis. Okay, any questions about the data? Oh, sorry, the formulation.
There's one question, but more on the, I think it's more of a clarification, how to determine the price elasticity.
Yeah, so that will be part of the estimation, right? So once you estimate Q, let's say one of the features will be price. So you will be able to estimate the price coefficient or the distribution of the price coefficients, and then you can estimate price elasticity, right? So actually, yeah, we did that in our numerics. So after you estimate Q, you can estimate price elasticity just as like using the standard definition. So it's possible to do that.
Sure.
Okay. So that's my loss function. And I guess the key challenge I want to point out is if you just try to solve this particular problem. So here you see there are no constraints on xis, right? Only constraint is Q, which is not a constraint. It's just saying it's a valid distribution. However, if you just try to solve this problem, you quickly run into an overfitting issue. Okay, because the unobserved factors make the model overparameterized, or I have too many degrees of freedom. Okay, so just as an example, in the sort of, again, real world study that I'll talk about, we had around 13,000 unobserved factors, only even if you just have 10 products and 2 features. Okay, so we had thousands of stores, and that's why we have so many unobserved factors, right? So because unobserved factors, remember, is for J and T. J is a product, T is a store. I have one unobserved factor for each product in each store. So if I have thousands of stores and even with like 10 products, this can quickly become very high dimensional. And what happens is if you have so many unobserved factors available, then if you choose any Q, you can perfectly fit the data. Or I can find unobserved factors that perfectly fit the data. So what does this mean, right? You give me any sales counts pattern, I can come up with a Q and Xi that perfectly explain. However, this is like sort of classic overfitting, right? This is because remember, my goal after I estimate Q and Xi is actually to predict demand in the future. So what will happen to the demand next week in the store, or what will happen to the demand if I add a new product or I change the assortment, right? You want to actually predict the demand. You don't really care about what's already happened because that's all observed, right? But what this is saying is if you don't constrain your unobserved factors, whatever you observe, you can perfectly explain. So when you try to predict in the future, that will sort of suffer very badly. And we also show this sort of empirically in the paper that if you don't constrain them, it can be very bad. But clearly the thing is we need to constrain these unobserved factors because otherwise you're just going to overfit. Okay, so how do we constrain these unobserved factors? We leverage ideas from the structural modeling literature. Okay, now some of you might be reminded of this endogeneity bias in sort of linear models or even nonlinear models, right? Which is sort of a key concern in sort of econometrics and causal inference, right? When my error term can be correlated with one of the observed factors, then if I just do kind of simple OLS, then my estimates are biased. So it's actually a very similar setting here. And we are going to borrow those ideas to constrain my unobserved factors. And that literature assumes that I have access to these auxiliary variables, which are called instrumental variables, such that if I condition on them, my unobserved factors have a mean 0. So in this literature, you think of these unobserved factors as random variables. So this is the expectation. So you assume that the conditional expectation is 0. Okay, so that's sort of the assumption in the literature. And this is nothing but what is called exclusion restriction condition. Sort of in simpler terms, this essentially implies that the unobserved factors are uncorrelated with my instrumental variables. Okay, so this gives you some conditions on the unobserved factors. In the previous formulation, xis can be anything, right? Like anything. But if I impose this condition, you're sort of constraining their values. They cannot take all possible values. Now, what is a classical example, right? So classical example is when the unobserved factor captures some unobserved product quality that is correlated with the price of the product. Okay, so if you ignore this unobserved factor, you might, if you just do sort of a standard demand estimation, you would see that the price coefficient is actually positive, which would mean as you increase the price, the demand increases, which is sort of clearly not right. And the reason is because you were missing this quality feature, right? So products that have a higher price also have higher quality, and that is what explains sort of the higher demand. And sort of the way to disentangle this would be to introduce IVs. An example IVs in this context is like the wholesale price, if I'm thinking of retail price here, or it could be like any kind of cost shifter, which impacts my cost, right? So the assumption is that these instrumental variables are not correlated with the quality, but of course they are correlated with the price, and that's like the standard IV condition. Okay, so again, I'm not sort of going into all the details here because this is sort of the sort of standard literature. There's like a big literature on instrumental variable estimation, and all we are going to do here is going to leverage those ideas for our problem. Okay, now like I have to sort of translate this condition into something that I can use. This condition into something that I can use in my estimation, because this is at the population level, right? I don't have access to the population. I don't know how Xi's are distributed in the underlying population. So what we do is we replace this constraint by the sample equivalent, which is again a standard practice. And the other thing that people typically do is instead of implementing a conditional moment, they use an unconditional moment, right? Which is you just look at expectation of Xi times Z is 0, which will also be true if this is true. So people typically deal with an unconditional moment restriction. And if I replace my population moment by the sample moment, it will look like this. You essentially look at the sample average, right? You sum over all J and T, you multiply Xi by the instrumental variable, take the average. So this should be averaged, but it's equal to 0. So I'm ignoring the average, right? And then you can write this more compactly as the following. You can just write it as Xi transpose Z is 0, where Xi is a vector of vector of these unobserved factors, and Z is the matrix of instrumental variables. Okay, so I think I said a lot here, but high level, sort of the idea is we want to capture this idea, this notion of instrumental variables from the structural modeling causal inference literature to constrain my unobserved factors. So that's sort of the key idea here.
Yeah, I don't see any questions though, but
okay.
Yeah,
cool. Okay, yeah, that's good. So yeah, and then finally, when we write this condition, of course, it's like in ideal, right? Or it's like in an ideal world, let's say, right? In practice, there are always kind of finite sample issues. So this is not going to be exactly 0, but all you want is you want to make this kind of as small as possible. So that's what we are going to do. Okay, so remember, this was my original formulation. Now I'm going to add a constraint on X's. Okay, so this is my constraint on X's. Now this, of course, is not Xi transpose Z is equal to 0, which is what I had in the previous slide. But you sort of take those vector of moments and you form this GMM constraint. So if you're familiar with generalized method of moments estimation, GMM estimation, this is exactly the sort of objective function there. So this is essentially telling you that you want those moments to be as small as possible. And the way we're going to enforce that is to upper bound it by some small positive constant. So G0 is going to be like a hyperparameter. So depending on how you choose G0, you can constrain your X's, right? So the smaller value of G0 you choose, the more you are constraining your unobserved factors. Okay, now sort of this is our final formulation. Okay, so one of the key things I want to point out here is, of course, it's a non-parametric because I am not making any assumptions on Q, right? Q is still arbitrary. Q can be any valid distribution. Sorry about that. Yeah. The second thing that I want to point out is we are leveraging instrumental variables purely as a regularization mechanism. Okay, so I mean, regularization, right, is this idea in machine learning of you want to constrain the model complexity because otherwise you will overfit, right? So this is exactly that. This is like a way to constrain my model parameters. Whereas in the causal modeling, causal inference structural modeling literature, instrumental variables are used to recover parameter estimates without bias, right? That's the key focus there. In this work, we are not making any such claims. The focus is still purely on prediction. Okay. However, we are still using the same mechanism as you do there. So we think that this is sort of one of the first works that tries to sort of merge or sort of falls at like the intersection of these two literature where we use instrumental variables as a regularization mechanism. Okay, but again, there's no claims here on sort of causal estimates or anything. This is still purely prediction. And G naught would just be like a hyperparameter that you tune in sort of, if you're familiar with lasso regression, right? Like you have this lambda, which is a hyperparameter. Similarly, you have G naught here. So you tune G naught depending on how much data you have to maximize your prediction accuracy. And finally, I think I briefly hinted at this, that even though in my data description, I said I only have access to a single data point for each store. In practice, I could have repeated observations for each store, right? Which is like, say, week 1, these were the sales in store 1. Week 2, these were the sales in store 1, and so on. And it's very easy to accommodate that kind of data in my loss function because you just sum over the weeks also. You sum over the stores, you sum over the weeks, you sum over the products. Like it's sort of very natural to do it. And the reason I'm saying this is because this is kind of one of the differentiating factors of our work from the structural modeling literature. Okay, which actually sort of takes me nicely into a sort of quick summary of existing literature. But I just want to see if there are any questions at this point. So this is sort of our sort of final formulation.
Nothing I see immediately. Any question? Yeah.
Okay.
But I have one question myself. So, how do you take care of these? So, what are we trying to do? Are we trying to, for a given data set, trying to find out the best fit and use this for future?
Yeah, the goal is prediction, right? But the way you do it is like you have a historical data, right? You fit your model, but you don't want to overfit, right? So you want to constrain the model complexity. So you want to fit, to kind of explain the data that you have, but the goal is, of course, always prediction or generalization. So yeah, so I guess maybe best fitting is slightly sort of ambiguous in that sense. Yeah, the goal is not just to purely explain the data that you have, because that you can do in the previous formulation if you don't constrain size. So the reason we add this constraint is precisely because I now want to make predictions. So maybe here we should not, yeah, you're probably right. Maybe I should get rid of best fitting here. Here you want to solve this optimization problem, and then you use the estimated Q and Xi to make predictions in the future.
So how does this differ from, say, a neural network or any of this? Because there also pretty much try to do the similar things where you estimate these parameters.
No, yeah, that's a good question. Yeah, so yes, you can think of neural networks as another way to sort of forecast demand or predict demand. So one nice thing about choice models like this MNL and
model substitution
of MNL is that there is some structure. So it helps you to make these decisions like pricing and assortment. And there's so much literature on that, right? Whereas with neural networks, actually, I mean, there is some work that is trying to, that is looking at using neural networks to predict demand and then also optimize like assortment decisions. But currently they don't really scale because, I mean, these neural networks are complex and you come up with like an MILP formulation, so it doesn't really scale. But so that's why we sort of focus on choice models, in particular mixture of MNL. But so that's sort of one response. The other response is one of the messages of our works is that we think of these xis as kind of adding a layer on top of any existing model, right? So suppose you have a neural network model. A neural network model is also only going to use observed features as inputs, right? You're going to pass in the price and all the, let's say, observed inputs. So potentially, I can also add unobserved factors to that model and improve the performance. Now, we don't demonstrate that, but that's like the conceptual idea, that we think of our paper as sort of having a layer on top of any prediction model. So you have a baseline prediction model. It could be neural networks. It could be choice models. You add this layer of xis on top, and then that can give you improved predictions. And that is sort of I mean, that hypothesis makes sense because in practice, there's always going to be unobserved factors, right? No matter how much data you have, you cannot capture everything that the customer is looking at. So there's, of course, you have to kind of do it in the right way, and whether or not it works, sort of empirically, is to be tested. But at least conceptually, that's what we want to say. That we think of this as kind of and I don't know if I probably have time to go to the details of the estimation, but the way we actually estimate our model, you can immediately see that it can be, you can just switch out the choice model and put in a neural network, and everything will sort of go through. But I think in the interest of time, I won't have time to go into the details of the estimation. I'll directly go to the results because I think that's more interesting.
Sure.
But that's a very valid question, and some of the reviewers also asked us. So yeah.
Sure. And just a follow-up question, a very short one. So how do you differentiate between unobserved factors in short term versus long term? So there are different kinds of unobserved factors, right? Some are very short term orientation, and some are something long term. And it really depends on your training data set, I guess the answer is.
Yes, no, that's a great question. Yes. So again, it will be, I'll mention that in my real world study, but at least there we looked at kind of short-term unobserved factors. So like for the next few weeks or a month.
Got it.
Because one thing that maybe I'll talk about it there. But yes, but you're right about that. That it's important to differentiate between short-term and kind of long-term.
Sure.
Factor.
Please go ahead.
Yeah. Okay, so yeah, so I guess I do want to talk about this slide maybe quickly. So if you look at existing literature, like I said, in operations, there's a growing literature on non-parametric methods, but all of these papers ignore these unobserved factors, right? So that's sort of our key contribution. Like you have this kind of ranking-based models, tree-based approaches, machine learning approaches, but all of them ignore unobserved factors. And like I said, one sort of conceptual contribution of our work is we can think of adding unobserved factors to any of these baseline models. So we demonstrated for the mixture of logit model in this paper, but maybe future work can look at these other approaches. Now, for the structural modeling literature, again, I won't sort of go into the details of all the papers, but what we can actually do is classify all of the existing works along 3 dimensions. Whether or not they allow for non-parametric mixing distribution or they assume a parametric distribution, whether or not they allow for these imperfect market share estimates, which I mentioned at the beginning of the talk, right? Depends on how big your sort of market size is, and whether or not they can account for sort of varying assortments in the same store, which again, like I said, is very standard in kind of operational settings, right? I have stockouts, I have changing assortments, so I need to account for that. And like sort of you can see from the table, our method is the only one that can account for all of these practical issues. Existing work can maybe account for 2 of them, but not all of them. Okay, so that's sort of how our work is differentiated from existing work. Okay, now, so how much time do I have? Maybe I'll just spend 5 minutes on the estimation. I think then we'll have time remaining for the numerics. So okay, so great. I come up with this formulation, but the main sort of question would be, can you actually solve it, right? Like if you sort of stare at this carefully, you see that the Q can be any distribution, like I said, right? So think of all possible distribution. It's like an infinite dimensional space. So how can you even think of solving it, right? The key insight that we have is if you try to sort of jointly optimize over both Q and Xi together, it's sort of very complex. However, if you fix one of them, so if you fix Q and optimize over Xi, or vice versa, you fix Xi and optimize over Q, the problem actually becomes a lot more tractable. So that's the idea we use. And this actually goes by alternating minimization or alternating descent. So this idea is actually standard in optimization. So what is the idea? Suppose I have an objective function which involves two variables, let's say u and v, and both of them could be constrained. Okay, the way I solve this, or one way to solve this, is the following. You initialize some values for both variables, and then in each iteration R, you do the following, right? First, you fix your estimate of V to be the current estimate, and then you just optimize over U. You get your new estimate, let's say UR. Then you optimize over, you fix U to be the new estimate, and then you optimize over V. Okay? And then you keep repeating this in each iteration. So optimization algorithms are typically iterative, right? Gradient descent, any kind of first order method. So this is also an iterative algorithm where you alternate between these two problems in each iteration. Okay, so this idea has been used extensively in machine learning and recommendation systems for large-scale optimization, right? And sort of one of the nice properties of this algorithm is when you look at this subproblem where you want to optimize over one of the variables, you don't have to solve it to optimality. All you need is what is called an improving solution. So like in this problem, suppose I find some UR that strictly decreases my objective value. So this is my current objective value. You find a new U or UR which strictly decreases your objective value. And why am I saying decreasing, right? Because you're minimizing. So you want to keep decreasing your objective values. So you can just do like a gradient descent step, right? So gradient descent, we know if you choose the step size properly, it will definitely decrease your objective value. So you can just do a gradient descent step, and that will give you a better solution, right? So in practice, this can make it sort of very scalable, right? Like these iterations are going to be very fast, and then you can do lots of iterations, like hundreds and thousands of iterations to get like at a sort of a good quality solution. So that's the idea that we are going to leverage. And in our context, what are the two variables? Q and Xi, right? So I want to think of two subproblems. One is when you fix the Xi to your current estimate, let's say some Xi R minus 1. So here you want to update the mixing distribution. Okay, now if you think of, I didn't add the constraint here that Q can be anything. But now what happens is everything becomes observed, right? So when I say that my Xi is equal to something, some estimate, essentially it means all the features are, or all the factors are observed, right? It's just a different way of saying that. So, and this is exactly the problem that previous literature has looked at, right? That everything is observed, you just find Q, the best Q. So we can use existing literature to solve this problem. And however, there is kind of one caveat that it is still an infinite dimensional problem because I still have to search over all mixing distributions. However, this is exactly the problem I worked on in one of my previous papers. So we just kind of leverage that method. Okay, now I think I'll skip the details there, but essentially, like I said, the idea is you can use existing literature to solve this problem. Now, the next subproblem is when you want to update your Xi. Okay, so now your Q is fixed to something. Okay, whatever is your current estimate, it's fixed. Now you want to update your Xi, and then you have this constraint, right? So this was this GMM constraint that I had. And it's sort of not hard to see that this will actually be a non-convex problem. But the constraint set will be convex. And also, it's extremely high dimensional, right? If you recall, the number of unobserved factors could be as high as like 13,000. Right? So it's important to kind of solve this efficiently. And sort of we leverage the problem structure to come with like a sort of closed form update to get an improving solution. Okay, so again, I don't have to solve this optimally. All I need is like an improving solution. And we can do that by sort of leveraging the structure of the problem. So again, I'm not going into the details, but I guess going back to Devji's question, here is where you can see potentially if you had some other baseline prediction model, this step will look different, right? So instead of Q, you will have like, let's say a neural network or the parameters of the neural network, but everything will be observed. So conceptually, you can use existing methods to solve this part of the problem. Yes, this part of the problem will be something that needs to be determined whether it can actually be solved reasonably efficiently. Now, yeah, that I think really depends on the structure of the model. But as long as we can come up with some kind of improving solution, the same idea can be used to potentially improve the performance of any other baseline prediction model. So um, yeah, so I'll skip this slide, the convergence guarantee. I think I'll probably skip this also. Let me just sort of go to the numerics. Okay, so yeah, we have some additional theoretical analysis that are different, that sort of gives insights on how our work is different from existing literature. In particular, this BLP estimator that I talked about. But I think, yeah, sort of in the interest of time, I will just kind of focus on the numerics where we compare our method with existing benchmarks, right? So here we look at a simulation study where we talk about price indigeneity. Okay, so what's the idea here? You have a similar utility model like before, but now I separate the price and the other features. So I have price as one of the features. These are all the other non-price attributes. This is my unobserved factor, right? Which is now correlated with the price. So this could be like, for instance, product quality. Okay, and then of course, this is just sort of, we generate the data sort of independently of each other. We set the price as the following. So we first generate the X, the instruments, and the X's, and then we set the price in this way, like a weighted combination of the instruments, the non-price attributes, and Xi, right? So this introduces correlation between Xi and P, right? Because, yeah. So this is, again, this is simulated data, so I can simulate any kind of data generation process I want. And then we sort of generate sales counts for different mixing distributions for like 25 products and 400 stores. For BLP, we use this Python package called PyBLP, which has like sort of state-of-the-art optimizations and so on. Like, so BLP has sort of many issues if you just implement it as is. So this work kind of tried to address some of those issues. So it's like sort of like the state-of-the-art in terms of estimating BLP. And then if you remember, for our method, we need to set G naught, right? So G naught is how much the moment condition is satisfied. Now, in this setup, you know that in the ground truth, the instruments and the X's are in fact uncorrelated, because that's how I'm generating them, right? But in the real world, you don't know, because, like, again, if you're familiar with instrumental variable literature, you always have to justify that this is like a valid instrument, because there's no way to test it. But in the simulated setting, I can. And so we just set G naught equal to 0 because that is true in the ground. Again, what I want to talk about here, I want to talk about the two key aspects about our method, right? So the first one is how imperfect market shares affect performance. So if I have, so these are the number of transactions in each store. So 1K is 1,000, 5,000, 10,000. And true shares means it's like a lot of transactions, or like, let's say, an infinite number of transactions. So this is the performance of BLP. Now, what is it? This is out of sample KL divergence. KL divergence is like a standard metric to measure prediction error. So this is actually lower is better. So this is prediction error, not accuracy. And what we see is our method sort of is significantly better than BLP whenever there is finite sample error, right? So when you have lots of transactions, like we are comparable, but when you decrease the number of transactions, BLP suffers significantly, whereas our method is kind of robust. Okay, so that's another setting. It's like an order of magnitude improvement. The other issue with existing approaches is that they can suffer from misspecification, right? So again, this is something that I mentioned in the talk. BLP assumes that the ground truth is Gaussian or normal distribution. But in practice, you don't really know. So this is the Q, right? The Q, the ground truth Q, you don't know what it is in general. BLP assumes that it is Gaussian. But again, it's a simulated setting, so I can try different Qs, right? So we try a mixture of 4 Gaussians or a mixture of 2 Gaussians. And you see, again, that the performance of BLP suffers as you increase the misspecification, whereas our performance is still robust, right? So this is a great thing about non-parametric methods, that they don't depend on the ground truth. Like no matter what the ground truth is, they can kind of adapt to it, of course, given that we have enough data. Okay, so in the final sort of 10 minutes, I want to actually go back to like the initial motivation, which is to predict weekly product store level demand. Okay, so to actually solve this problem, we do have access to similar kind of data, which is this IRI academic data set. So this is a data set that is used a lot in this kind of demand prediction literature in the retail context. I've also used it in previous papers. So the data format here is exactly what I had in the beginning, right? So yeah, weekly sales transaction data for consumer packaged goods in like 30 product categories. I'll show you some examples of product categories. Each transaction specifies the week, the store ID, which product was purchased, how much the price was, how much was purchased, what was the price, and whether or not it was on promotion. So I think there was one question about promotion, price or display promotion. That will just be a feature in our context, right? So in this case, the utility of the customer has the following form. So I have customer I, product J, store T. This is the same as before, but now I have an additional dimension, which is the week, right? So I have, for each store, I have data over different weeks, but that doesn't really change much in our formulation. So this is like an intercept term, which is like some kind of preference for the product. This is the price of the product, J in store T in week W. This is the promotion indicator. So this is going to be binary, 0 or 1, whether or not it was on promotion. And of course, this is like your Gumbel error term. So, okay, so again, this is like exactly the data that I had in the beginning, just like separated out for different features. So what we first did was to use the state-of-the-art method to predict demand when all the features are observed, right? So here there is no xi. You see there is no xi here. So everything is observed here. So we use like one of my previous papers, which we established was like the state-of-the-art for demand prediction in the presence of observed factors. So this data set is very big. So we just focus on 2 weeks data, and then we predict sales for the 4th week. And this is what we got. Okay, so this is again the KL divergence, which is a standard sort of error metric. So lower is better. Okay, and these are different product categories. So in the paper, we have a few more product categories. But just an example, like coffee, deodorant, toothbrush, cereal, toothpaste, and so on, right? So these are some of the product categories in the data set, and this was the performance, okay? So this is like the benchmark that you have to beat, right? So the question is, can you do better? And of course, the whole message of the talk was to account for unobserved factors, right? So that's what we are going to do. So we are going to introduce unobserved factors, right? So I'm going to add this xijt. And I guess this again goes back to these questions. So here, the way we are going to add, excuse me, xijt is I don't have a xijtw. I just have xijt, right? So this is time invariant. And the reason we do this is we want to, first of all, make predictions, right? So if you want to make predictions for the future week, you need the xi to be the same, because if the xi is changing across weeks, I don't know what the xi is going to be the next week. Okay, and because of that, this kind of model or this kind of specification, I should say, is more suited for short-term predictions, because in the short term, like let's say a few weeks, maybe you can assume that the unobserved factor does not change much in the store, right? But if you're looking at, let's say, start of the year versus middle of the year, the store environment can change a lot, right? The kind of promotions that there are, the location of products in the shelf, all of that can change significantly. So then we need to sort of look at a different specification. But here, like I said, we use data from weeks 1 and 2 to predict for week 4. So they are all kind of like within a month. So we believe it's like a reasonable assumption, right? And of course, the results will tell us whether this was a good assumption. Okay, so Devji, that's sort of related to your question.
Yes.
Okay, so this was the benchmark to beat. Okay, now how do I estimate these unobserved factors? It turns out that any of the benchmarks or existing methods in the literature don't work, because this BLP, which I didn't have a chance to discuss in detail, they cannot be implemented because my stores have stockouts, right? My assortments are changing, and actually BLP breaks down in those settings. So all we could do is like sort of just use our method that we proposed. And we used Houseman instruments as remember, I need to have instrumental variables in my formulation. So we use what are called Houseman instruments. And these are, again, standard in the literature. So what are some examples of Houseman instruments? It would be the average price of the same product across other stores, let's say in the same geographic market or in the same chain. So here, actually, we look at multiple chains, not just one chain of stores. So what I want, remember, is an instrumental variable for J and T. So clearly it cannot be the same store. So that's why we are saying it's the average price of the product in other stores. Okay. Now other stores could be in the same area or in the same chain. And the good thing about this is all available in the data set, right? The data set captures the variability of prices across stores. So I don't have to go out and get additional data, right? So all of this information is available in the data set. So that's why when I said in the beginning that this is with the same data, that was the reason. Okay. So we add these kind of Houseman instruments, and you see it's significantly lower, right? So lower is better. So you see across these product categories and a few others, our method is significantly better, and it could be up to 63% better. Okay, so it is really, really important to capture these unobserved factors. So kind of let me skip this. And like I said, in practice, we just don't want to stop at predictions. We want to go and make decisions based on these predictions. And like this slide is going to actually talk about the impact of the decisions. Okay, so what is this? So on the y-axis, I have each product category. So like coffee, toothpaste, and so on. And each X here is a store. Okay, so each X is a store. And the red X's are talking about the posterior mean promotion sensitivity in each store when you ignore unobserved factors. Okay, so you think of like the posterior distribution of the sensitivity for customers visiting that store when you ignore unobserved factors, and the blues are under our method, the same analysis, right? So there are two things that you see. The first thing that you see is our distribution is a lot more concentrated, right? All of the blues are close to each other, whereas the reds are spread out. So what this is telling you is that the benchmark method that ignores unobserved factors is attributing store level heterogeneity to customer heterogeneity. Okay, because the reason that you have variation across stores is because you are thinking that different customers are visiting different stores and they have different sensitivities to promotion. But the reason you are saying that is because you are not capturing these store fixed effects. once our method does that, you actually see that there is not a lot of variation across customers in different stores. So this has big impact for promotion decisions, right? So the benchmark method is going to say that you should sort of have heavy promotions in some stores and not promotions in other stores. Whereas our method is saying actually you should have similar promotion decisions across stores. And interestingly, you see that so a lot of these promotion sensitivities are actually negative, right? That doesn't make any sense, right? Because of course we expect customers to respond positively to promotions, but the benchmark is saying a lot of them are negative. And the reason is precisely that you're not capturing unobserved factors, right? So you're saying that these can be negative, but that doesn't make sense. So this is also another limitation of ignoring unobserved factors. Okay. Yeah. So I guess yeah, I'm sort of almost out of time, so I'll just finish here. Like the key takeaways: accounting for observed factors is critical. You get better prediction performance even with the same data, and it avoids misattribution of store level variations to customer heterogeneity, which leads to better pricing and promotion decisions. I didn't have a chance to talk about the theory aspect of this, but like finite sample errors can significantly impact performance. And this is important for slow moving products or categories, right, where you don't see a lot of sales. And of course, parametric methods can suffer from misspecification. This is well established in the literature, and we also kind of add to that. Okay, so yeah, I'll stop here. Thank you for all the questions, and I'll be happy to take any more if we have time.
So there are a few questions. Thank you so much, Ashwin.
Sure. Yeah.
There's one on how often do you recommend to train or retrain these models, like for operation demand planning?
Yes. So that's a great question. So yeah, we don't directly kind of address that aspect, but yeah, I think in practice, what happens is you kind of train these models, yeah, maybe every few months or but yeah, I think it's hard to sort of give like a sort of a standard answer, because I think it really depends on the specific industry, sort of the customer demographics, whether you need to train them more frequently or kind of less frequently. Also, the product category, right? Is the demand like very variable or more stable? So, but yes, I guess the bottom line is you would need to kind of periodically retrain these models to capture the kind of latest trends and preferences.
Okay. There's a follow-up question like, has this model been compared? I think it's similar to what I asked before with machine learning or RNN approaches and so on.
Yeah. So no, because like I said, our message is not that this is like the best forecasting method out there. Like no paper or method can really make that claim, right? Because there are like infinite number of methods out there. So yes, there could be something else that can be better than what we did here. But the contribution we believe is more like this idea of incorporating unobserved factors, right? So any kind of model that you use in practice, it's just using the observed factors, right? But the idea here is, because there are always unobserved factors in practice, if you can account for them in the right way, you can potentially boost the performance of any baseline model, right? So if you are already better, you can be further improve if you use neural net. Now, of course, that's conceptual. Empirically, it should be tested out. But yes, the claim is not that this is better than like the state of the art RNN or transformer or whatever. That's not the case. Yeah.
Got it. There's a question from Ramji. It was asked earlier. On unobserved factors, say store in South India likely has a lower price elasticity or even a higher substitution, but unlikely to happen in North India. So how would you sample? So using a sample, how would you predict it for a population? So I think it's more questioning the universal nature of this algorithm. So is it only based on you can only draw inferences on the sample that you have chosen?
Yes. Yeah, I think so. Like so that I think is kind of captured in the data, right? So like if you have a store in different parts of India, let's say, like the issue of price sensitivity, that should show up when you estimate your mixing distribution. Or especially when you, let's say, not Q, when you estimate these kind of analysis, right? So I think maybe the question is, my Q does not depend on particular stores. That is true. Like we are assuming that the distribution of preferences is the same across the population. It's not time varying, it's not store varying, yes. But like some of the heterogeneity in terms of customers in different stores, this you can capture that using like posterior analysis, right? Like,
Sure.
so that can give you a sense of, yeah, like which customers are more price sensitive or promotion sensitive and so on.
Yeah. We're running out of time. I want to take one final question. Maybe there's a question also on, do we need to check stationarity in data? And I guess no, because this is free.
I mean,
or you will check that.
no, we don't check that, but I guess implicitly we are making that assumption because we're assuming Q is fixed, right? Q is not changing over time. So yes, so this would be like for short term or medium term kind of analyses. Yeah, like you have, that's why you have to kind of periodically retrain, right? So you sort of, if the distribution has completely changed, then you need to kind of retrain your model. Yeah.
No, I think it was fascinating talk, Ashwini. I think you took a lot of patience to take it for
No, thank. I probably had too much planned. I had so many other slides.
No, I think all the questions were very relevant, and I
yes,
think
definitely. I am definitely grateful for all the questions.
Yeah, it was fascinating discussion, conversation. So hopefully you can join us in person sometime next time when you're here.
Definitely, yeah. Next time I visit India, yeah, maybe I can. I haven't been to any of the IAMs actually, so
great. So it's a good opportunity.
Yeah,
so thank you all for joining this evening as well, and hopefully to see all of you in another CTL webinar.
Yeah, thank you so much, everybody. Like, yeah, really appreciate all the questions. It's good because it's virtual, so at least it's interactive. Otherwise, I'm just kind of speaking for 1.5 hours. So I'm grateful for all the questions. Yeah,
thank you.
And thanks, Debjit, for again inviting.
Thank you. Bye-bye.
Yeah, bye.